Question 2. Prilocaine is used as an anesthetic in dentistry. Figure 3 shows the structure of prilocaine. Draw a circle around any chiral center in figure 3. I see what they did here. Any chiral center, bracket S, so it makes you think there's going to be more than one. But that's not the case in this question. There's only one. And a chiral center, remember, is when a carbon atom has four different groups attached to it. So in this case, it's going to be this carbon, because this carbon has this C double bond O. It has a CH3 attached to it. It has a NH and it has a hydrogen. So that's four different groups. CH3, C double bond O, a H, and an NH are all different groups. So yeah, it has four different groups attached to it. Identify the functional groups in the prilocaine molecule. Well, actually, that's not going to be clear for the examiner. It said just show a circle. So yeah. So we know that amide is ester CH3 R C, and it's going O R. It's doing that supposed to ester. It's not going to be an ester. Amide and amine. Yep, it is attached to a NH, and it also is attached to CNH, C double bond O. So there is going to be an amide functional group in a prilocaine molecule, and there will be an amine in the prilocaine molecule as a functional group. And then it says prilocaine is completely hydrolyzed to give a mixture of products through the structure of two organic products forming complete hydrolysis. So hydrolysis, what are we doing in the hydrolysis? Well, we're adding water, right? And so what's going to happen is we're going to have our normal molecule, so CH, NH, CH, H, and then the NH, and then the CH, which is attached to obviously methyl group, CH. Then we've got what? C double bond O. And now here's a different part. Instead of this bit, this bit's going to disappear, and we're going to be left with an OH. Remember hydrolysis using H2O, right? So this HO is going to bond to the C double bond O, and then what we're going to be left with is obviously this. So here, and it's going to be bonded to an NH. For an extra 2 hydrogens, but the nitrogen is now positive. That's what can be formed. This first product, and then this as a second product, which this is not part of the molecule. This is just a different. This is the second product we're forming. And then 2.4. Isomer F is an active compound in the medicine ibuprofen. In the manufacture of ibuprofen, both isomers F and G are formed. An enzyme is then used to bind to isomer G and catalyze its hydrolysis. After the products of hydrolysis of G are removed, a pure sample of isomer F is collected. Explain how a structural feature of this enzyme enables it to catalyze hydrolysis for isomer G, but not the hydrolysis of isomer F. So anytime we think about enzymes, active sites, right? So why can this enzyme, what is the how a structural feature of this enzyme enables it to catalyze hydrolysis of isomer G but not hydrolysis of isomer F? Well, it's all down to the active site. Enzyme has an active site, and the isomer G, and enzyme has the active site. Enzyme has the complementary shape for G enantiomer. We'll just say enzyme has a complementary shape, because what we're talking about, we already know we catalyze hydrolysis for isomer G but not hydrolysis for isomer F. It just wants us to explain how the feature of it. Well, enzyme has an active site for one mark, and then the enzyme has the complementary shape for another mark. And that's the end of question 2.